Welcome back to day 2 of BlinkOn 16. Again, I'm Tab Atkins-Bittner, Web Standards Hacker at Chrome, and your MC for today. I had a lot of great conversations yesterday, and I want to engage in even more today. BlinkOn presents us with a special opportunity to meet and catch up with people in the Blink community who we wouldn't normally be able to meet. That's why I'll be giving everyone a call to action before we part ways for our first round of breakout talks today. Until then, I want you to start thinking about one or two people who you either have a question for, haven't talked to in a while, or haven't met before, either in person, remotely, or both. But that won't happen for a little bit. Until then, enjoy today's lightning talks, again hosted by Kentaro.
Hi, I'm Haraken. So welcome everyone back to the BlinkOn Lightning Talk session. Are you more excited? So I want to celebrate the BlinkOn Lightning Talks as always with a party pop. But I have nothing, so I have really nothing, right? So 1, 2, 3, and blink on. Amazing. I got a party pop. All right, so let's crack it. Yay. So today, we have another 13 lightning talks. And as always, I asked each speaker to insert one point where they can get a storm of applause. So please find that point and send a round of applause and heartwarming messages in the text chat. So the speakers are also watching this session. All right, so let's get started.
Hi, my name is Don Ferlino. I'm an engineer on the Chrome team, and today we're going to be talking about debugging Chromium with LLDB. LLDB is the debugger associated with the LLVM toolchain. The reason we're covering LLDB today instead of GDB is because years ago when I was debugging my first crash in Chrome, I came across this nice tutorial by an ex-Chrome engineer about how to use LLDB to do so, and I thought it was a really good tool, and I'm here to continue the trend. So why a debugger in the first place? What's wrong with printf debugging? Well, the code path you end up taking when doing something on the web is often very different than the one you might think you'd take by just reading code search, and that's because there's a million different places where you can make incorrect assumptions along the way. And so for some of the trickier code flows and some of the trickier cases, using a debugger is the only way to know exactly for sure what code is executing. The second thing is when you're debugging a tricky crash, it's always hard to know what state you might need to capture in advance with printf. So this helps you avoid the printf, rebuild flow. Setup is pretty straightforward. On macOS, you're good to go as long as you have Xcode command line tools installed. And for Linux, you just need to apt-get LLDB most likely. For your Chrome build, you'll just need 3 ginargs. You want a debug build with the highest symbol level available, which is 2. This will give you full frame variable access as well as code mapping. You'll probably need to adjust your ptrace scope as well to allow the debugger to actually control the execution in the Chrome process. Feel free to follow that Stack Overflow link for more information on how to enable that. We also have some good documentation on getting LLDB up and running in the Chrome repository. The main thing you need to do is create an LLDB init file and add these 3 lines to it. The second of which links to the tools/LLDB directory in Chromium, which has a Python script that does some Chrome-specific initialization stuff with LLDB. So now for a quick demo of using LLDB, we're first going to attach it to an existing running Chrome browser process, set a breakpoint, and inspect some of the contents of a navigation request. So for starters, we're going to run Chrome. I usually run it with a no sandbox flag, which helps when you're debugging renderers and the network service. We're going to, in Chrome's task manager, find the process ID of the Chrome process that you wish to debug, and then in a separate terminal tab, run LLDB on the Chrome binary, and attach it to the PID that is your target process. That'll spit out a bunch of output that shows the process being frozen and all the threads in it. And you can continue the execution at that point and set a breakpoint wherever you'd like. In this case, we're going to set it on the commit navigation method in the browser process, which is a common method that most navigations ends up touching. In Chrome, we'll navigate the browser to example.com, and we'll notice that the debugger stops in the first line of renderFrame host impls commit navigation method, and we can see all the code there and step through it by by typing next or n. Notice that this is the same code that code search shows us as well. It's just that now we're able to step through it line by line, view all the contents of the variables and all sorts of things. So a bit later on, we can run an expression with expr and actually view the navigation request variables, common params members, URL, and that'll spit out the dump of the GURL that is in that struct, and we can actually see that the underlying string is indeed example.com. So for a follow-up, you should now just feel free to use LLDB and explore around a bit. Step into functions and view the stack traces. You can actually watch variables and do all kinds of cool stuff. And for a quick resource for all the things you can do in LLDB, feel free to Google search LLDB cheat sheet. Thanks.
Hello, this is Jacobo from Igalia with an update on my recent accessibility work in Chrome. You may know that a lot of our work to make the browser accessible is to make sure that everything can be used with only a keyboard. For example, for a native HTML slider to be accessible, we needed to accept key presses to modify its value. The convention is to use the arrow keys for that. And if web authors build a custom widget for that purpose, accessibility authoring guidelines explicitly recommend to implement keyboard event listeners for increase, decrease, etc. Attached to the arrow keys and set the area role slider. So from the point of view of a keyboard user, it works just the same. But there are devices which don't have a keyboard and users who cannot use a keyboard either, so some assistive technologies rely on gestures or voice commands. To implement them, the different accessibility toolkits have Actions APIs. A UI component is allowed to expose a list of operations, which can be different for every component. Going back to the slider example, this would expose actions named increment and decrement. We already have some support in place for these two actions in Blink. If applied to a native HTML slider, the increase and decrease actions will work as expected. A custom widget with a role slider will also expose those actions, but they won't work yet. Why? Because the logic for these actions is implemented in JavaScript and is triggered by key press events only. The solution proposed in the Accessible Object Model effort to make actions working on those custom widgets is synthesizing the correct events for the website to consume. If the increment action produced the same events as a right key press, this is key down and up, the website would react to them and increase the slider. We are currently capable of synthesizing up, down, left, and right keyboard events in response to increment and decrement actions, depending on the slider orientation and text direction. This is hidden under a flag. We are currently working on the context menu and scroll page actions to make them synthesize the corresponding mouse or keyboard events. There are more kinds of actions that we haven't implemented in Chrome yet, but we might consider adoption of Actions APIs before going for them. Finally, we are reviewing the different platform accessibility implementations we host in Chrome, checking if we are exposing actions where it makes sense. Otherwise, these features won't be available to AT implementations, and it would be a waste. That's it. Thanks for watching. Goodbye.
Hi, my name is Victor, and I work on Chrome Developer Tools. I want to tell you about our plans for modern web debugging and give you one example of what it's aiming towards with the async stack tagging API. And to do so, here's a quick story. Alice is creating a web application she's altering. This web application will be fetched and presented to users by a browser where it's running. We know how this works. And Alice picks the most appropriate architecture for her case, and also minifies and then serves the code by deploying it. And this is all pretty magical, and the end result can end up looking nothing like what she started with. But Chrome DevTools happens and runs in the runtime context. It could be hard to make the right decisions on what to fix and what to optimize because the end result can be so different, and that's where DevTools is running. And this is the friction in the development experience that we're aiming to solve. But some of this solution already exists, source maps, but to solve this holistically, we need more. For example, more extensions that enrich DevTools with information about the original code, rather than just creating new panels that sometimes duplicate built-in ones, like the profiler or the elements panels. So one such incremental step is the async stack tagging API. Here's what we plan to improve with it. Suppose you have a function foo that calls bar, which doesn't call buzz, but instead some scheduling library schedules buzz for later. And Alice has decided that in her particular case, it's important to use this scheduling library for state management, and it's not using stuff like set timeout. So if a bug sneaks in, then it's hard for Alice to debug this because from her mental model of the application, it's foo calling bar, calling buzz. But this is different from the browsers in the debugger's point of view, where the call stack contains some obscure calls and then just part of her code from her perspective. There are no breadcrumbs to connect the steps leading to an issue. And the sync stack tagging API aims to solve exactly this by enabling task attribution in user space. So by marking where these kinds of async operations are scheduled, started, and finished, DevTools has enough information to then stitch these together in the debugger and the console and everywhere else call stacks are shown. And this is available in the latest canary builds under flag. Check out the CR bug for more info. So the modern web debugging project's North Star is reduce friction by enabling developers to debug in profile from the authored perspective. And this means debugging in terms of the authored sources and the project structure, debugging in terms of the developer's mental model of the application runtime, and also debugging and understanding framework performance and context. I'm looking forward to your feedback. Reach out to me or to the Chrome DevTools mailing list. Thanks.
Hello, BlinkOn. I am Felipe from Igalia, and I wanted to talk a bit about some of our work on the Web Extensions API. As you know, the next iteration of the Web Extensions API is called Manifest v3, and one of its main features is declarative net request, which allows the extension to declare a set of rules and then ask the browser to evaluate and modify network requests on its behalf. Static lists of rules are bundled and distributed with the extension, and other rules can be added and removed dynamically one by one, but in a much smaller number. So, since the most useful lists have tens of thousands of rules, they have to be bundled statically with the extension. The problem that we are looking at happens when one of these static lists bundled with an extension includes a rule that turns out to be harmful after it has been distributed to users. This happens every once in a while, and usually nowadays extension developers take a short time to detect and fix these errors. Sometimes the problem becomes more widespread and more visible. For example, last year when an error in EasyList broke functionality in Google Docs. But still, also in that case, developers were able to get notified, fix the problem, and distribute the updated list within a day or so. Now, an unintended consequence of the move to v3 is that fixing problems in these static lists will become much harder, because static lists can only be enabled and disabled as a whole, and they cannot be changed. So if you need to modify a static list, you need to update the whole extension, which could take some time. And in the meantime, the web stays broken. You could disable that whole static list, but that will remove some of the main functionality of the extension. You could try to add a new rule dynamically with more priority that works as the opposite of the problematic one. But in that case, you risk side effects because your new rule does not just override the wrong one, but takes precedence over all those other tens of thousands of static rules. So from our point of view, it would be much easier to be able to simply disable the problematic static rule. And that's exactly what we've been working on. We are working on an API proposal to optionally add a collection of disabled rules at the point where the extension enables and disables static lists. We are discussing this proposal mainly on the Web Extensions Working Group, so if this sounds like an interesting problem and caught your curiosity, then please drop by and leave us your feedback. Thank you very much.
Hi, I'm Xiao from Igalia, and today I'd like to talk about measuring performance impact of your changes on Chrome OS. What do I mean by that? Let's take a look at motivations first. Say that a Chrome developer comes to you and asks the following: I just landed this CL could you test see if there's any performance regression in our target devices? Or then another dev says, I got this performance-related bug assigned to me, but I don't know where to start looking. So those are the motivations, and the TLDR of this presentation is, for Chrome OS, learn very well Chrome tracing and test. But let's take a look closer on the ideas behind. There are two techniques to address those developer problems. One, performance analysis, useful to understand the facts on how to use the device resources such as CPU, GPU, memory, and so on efficiently. Two, integration testing, to verify that everything is working well together. We'll show what's the process to use each of those techniques. For the performance analysis, our optimization process goes like this. Observe where the performance differs. For example, window animation is slow, tab dragging is lagging, and so on. In other words, define the critical user journey. Then collect performance data, getting execution trace basically. Do an analysis and build a theory of what's going on. Then you implement the optimization. After that, you iterate back and repeat this full cycle until the analysis step, where you'd ask, did we actually improve the running path? So for Chrome OS, you need to master your skills and learn Chrome tracing. Tracing is great. It lists all processes and threads and other OS aspects of tasks, IPC messages, and other important things as well. Alright, performance analysis done. What next? How to make sure, for example, that all my devices are being checked. That's why manual analysis can be really cumbersome sometimes. It's very expensive, prone to human error, and difficult and fast releases. So that's why automation within the integration test comes handy. Integration testing is critical. The process we use for that goes like this. Refine the test strategy to set the benchmarks, build the automated tests, deploy it to run, and generate the reports. On Chrome OS, you can use TEST, integration testing system for Chrome OS. TEST not only does performance testing, but is also a great end-to-end testing framework, supporting building, deploying, and running tests. TEST uses Go as a programming language for building tests. It's super fast for compiling code, and its static analyzer is great also. So, different strategies exist. We showed only two, but very powerful processes that's being used in Chrome-based projects. I hope you learned a bit about performance when developing Chrome. Thanks for listening and join BlinkOn.
Chrome Status is a database of web platform features, and it is the tool that supports working a new feature through the Blink launch process. Today I'm giving a lightning-fast tour of how to use it. Web developers can visit the roadmap page to see new features that are in an upcoming Chrome milestone. You can click to scroll further into the future or the past. Each card shows the features launching in that milestone, as well as pre-release features that are available behind a flag or as an origin trial. Over on the Feature List tab, you can see a list of all features and search them. Expand each feature to see a little more detail, or click the feature name to go to the feature detail page. Drilling into the feature detail page, you can see the most important aspects of the feature entry, including its description, motivation, documentation links, spec links, estimated milestones, signals from other browser vendors, and the feature owners. Lower down on the page, there's a section that you can expand to see every bit of information that we have about the feature. The third main tab is for the feature usage stats. You can see a list of CSS or JavaScript features sorted by how widely they are used, or you can sort by name. Click on the usage bar to drill into the timeline view that shows use counter numbers at the top and HTTP archive data at the bottom. Now let's sign in to see how all that information gets into the system. Signed in users can star a feature to get email notifications about changes to it. If you are signed in as a Chromium developer, you will see pencil icons that allow you to edit the feature entries. The editing page guides the developer through the stages of the feature launch process. For each stage, there's a detailed form with the fields you need to fill in for that stage. When you're ready, you can generate an intent email and then send that to the Blink Dev mailing list to get the LGTMs that you need to proceed. Signed in users also see a My Features tab. Every user sees a section listing starred features so that you can quickly get back to the features that you expressed interest in. If you're listed as the owner of any features, those appear here in another section. When one of the Blink API owners visits this page, they also see a list of features that have pending intent threads. They use the approvals dialog box to record their LGTMs and post short comments back to the Blink Dev mailing list. So there you have it. That's Chrome status. Blink developers have a huge impact as the web platform evolves faster and faster. Chrome status is part of how we do that in a way that is transparent, coordinated, and inclusive of our ecosystem partners. Feel free to reach out with any questions. See you online.
Hello everyone, my name is Nicholas, and today I'll talk about the Fedcm desktop UI. Federated identity is when people log into some website or relying party via an existing account from another site, an identity provider. I'm sure we've seen this on the web. Sign in with Google, with Facebook, with Twitter, etc. Federated sign-in is easy for users, and it is safer for them as it reduces the number of passwords needed. Some of these sign-in flows use third-party cookies. Three main use cases come to mind. First, there are widgets implemented via iframes that allow the user to directly sign in to a website via the identity provider. Second, showing personalized sign-in buttons requires knowing the user. Hence, this uses third-party cookies. Finally, the identity provider can sign out users by using iframes to notify the relying parties. These flows break once third-party cookies are phased out, unless some intervention takes place to allow them. A bunch of major browsers already block third-party cookies by default, and Chrome has announced it will do so in the third quarter of 2023. So a bunch of us in the web identity team have been working on tackling this problem while also thinking about the big picture of federated identity on the web. Our initial Fedcm API is an origin trial on Chrome 101 to 105. The origin trial started only on Android, but have implemented most of the desktop UI with a lot of help from Peter Kotwigs. We intend to start desktop origin trial on Chrome 103, but I wanted to give a preview of how it looks like as of the first few days of May. So now is demo time, with a caveat that a lot of UI polish is to be done before the branch cut. So first, we need to go to Chrome flags Fedcm and enable the feature, which might prompt you to restart the browser. Then we're going to go to our demo site. It'll show a prompt to log in on the right, and you can select the account you want to use. It shows you the privacy policy and terms of service, which you could click on. And now you can click on continue, and it shows verifying, and you are now signed in. Now let's say you come back to this site again, and you click on the account again, the one you just used, then it'll now show you verifying since it knows you already accepted terms of service. So please feel free to join us in the breakout session on the Fedcm API if you have questions or thoughts. Thank you.
Hi everyone, this is Xiao on the Chrome rendering team. Today I'm going to introduce a new feature in Blink that allows you to add render blocking resources to improve your page performance. And your reaction might be, wait, what? I know, if we search render blocking on Google, it tells us to eliminate them. But today I'm telling you that you should actually add render blocking resources if necessary. In fact, we have a new feature under development that allows you to make basically everything render blocking. The usage is pretty simple. If you have an element that downloads something, then just add a blocking equals render attribute to the element. And rendering will be blocked until the resource is loaded. You can put it on preloads, async scripts, style sheets, and etc. And if you want to try it out, it's behind the experimental web platform features flag. Let me show you an example of how to eliminate layout shifting when using web fonts. Without render blocking, we will first render the page with a fallback font, and then re-render when the web font is loaded. Since the two fonts have different metrics, everything shifts around. With this new feature, we can make the font render blocking by preloading it with blocking equals render. In this way, we won't render the page until the font is loaded, and there is absolutely no layout shifting. Now there might be a concern. If I make something render blocking, what if it blocks for too long? The answer is that we can also manually unblock it by removing the attribute. And this actually allows us to achieve different trade-offs. For example, if I want to use a web font and if the connection is fast, I prefer no layout shifting. But if the connection is slow, I prefer an early first paint and can tolerate some layout shifting. We can achieve this by setting a timeout that removes the attribute. Now we've seen that render blocking can actually be very useful. So let's go back to the eliminate or add topic. Is there a contradiction between this feature and the previous recommendations? My answer is no. If the resource is not critical, eliminate it. If it's inlined, inline it so that it will no longer be render blocking. However, if it's critical and cannot be inlined, for example, if it's a font or a third-party resource that you don't have control over, or if we prefer parallel loading of resources, then we should make it render blocking. The rule of thumb is use it only when necessary, only when we are sure that it improves the performance. Use it with cautions, but don't add it to everything. Thank you, and here are some links if you want to learn more about it.
Hello everyone, I'm Daniel from the Chrome team, and I'll be talking about the various map implementations we use today and if we should consider using Swiss tables. As quick background, Swiss table or Abseil's hash table implementation are intended to be a good default choice for map and set containers. Today, Chrome mostly uses stdmap and base flatmap. A quick grep shows 9,000 references stdmap and 3,000 references to base flatmap. Base flatmap is supposed to be a default container in Chrome. It has good memory usage with low per item overhead. On a 64-bit architecture, stdmap has 32 bytes of overhead per item, while base flatmap has no per item overhead. However, flatmap has drawbacks too. It's not well suited for containers with many items, since insertion and removal have ON performance. In most cases, this won't matter, but the performance cliff can be an unpleasant surprise. So how do Swiss tables compare? There's a lot of performance benchmarks already, so I'll skip those and simply look at binary size and memory usage. I wrote a small test file to compare binary size. Abseil's containers don't seem to fare too well here, with int keys and std_string values. If I flip that around to be std_string keys and int values, then the binary size numbers shift around somewhat. In fact, some of the functions are suspiciously small due to different inlining decisions by the compiler. If I try to benchmark a larger snippet, then things look different yet again. In fact, btree map looks really good now for some reason. Based on this, it seems like binary size should not be a primary criteria for selecting containers. The compiler's inlining decisions can make large shifts in binary size. Another interesting thing to note is that flatmap seems to consistently generate small code. This is in contrast to the last time we looked at the binary size impact, where stdmap actually generated the least amount of code and base flatmap actually generated the most. Moving on, how do we get an idea about memory usage? What if we just add some simple logging? Turns out this breaks lots of things. In particular, flat tree itself needs to be usable in a context-expert context for things like fixed flatmap. What if we use templates? This also doesn't work. Destructors can't be context-expert until C++20. Instead, I decided to just use a giant hack where I make a copy of the code for context-expert containers and instrument the original. And some preliminary results. This is a video capture of Chrome histograms in monitoring mode. Yes, we are doing something like creating and destroying 3,000 flat maps a second. I think this is largely an artifact of running histograms in monitoring mode. If I launch Chrome and leave it for 2 minutes idle, it only shows 60K recorded destructions. Don't get it wrong, though. We absolutely create a ton of flat maps. If I navigate to another page and check histograms, then the count balloons to something like 150K destructions. Careful observer will also notice that somehow the number of times flat maps are destroyed is going up faster than the number of times flat maps are created. I have no idea why. Some data around size. As you can see, most containers are pretty small. And some capacity numbers. Pretty small overall. I was trying to get an idea of load factor, but it doesn't work well when the numbers are this small. Anyway, there's still a lot that needs to be done. Even if Swiss tables are an absolute win, there's probably still gains to be had from unifying on a default container. Thank you. If you're interested, please get in touch.
Hi, my name is Wolfgang, and I'm an engineer on the Chrome DevTools team. I'm going to talk about measuring the usage of the Chrome DevTools protocol. Specifically, I would like to go into what and why we're measuring, how we're doing it, and the conclusions we're drawing from our measurements. Let me begin by quickly introducing the Chrome DevTools protocol, or CDP in short. Chrome DevTools communicates with the rest of the Chromium browser via CDP. CDP allows Chrome DevTools to instrument, inspect, debug, and profile Chromium. CDP is not limited to the communication between Chromium and Chrome DevTools, though. On the browser side, CDP is supported by all Blink-based browsers, and other clients besides DevTools are browser automation tools such as Google's Puppeteer or Microsoft's Playwright. And finally, Chrome extensions also have access to CDP and can use the functionality it offers. CDP is pretty powerful, and this has caused us to recently question whether untrusted Chrome extensions really need access to everything CDP offers. CDP is conveniently divided into functional domains. Within each domain, there are commands and events. Commands are functions which can be called by CDP clients, and events are emitted by the CDP host to inform CDP clients about something. At the beginning, we only had a very limited understanding of which CDP commands are actually being used by the various types of clients, especially in the case of Chrome extensions. In order to collect data and get an idea of usage numbers, we added UMA sparse histograms to log the usage of CDP commands. Sparse histograms map from a large, sparsely populated range of integers to an integer representing a count. We therefore first introduced a mapping from CDP command name to an integer by hashing the CDP command's name. This would be used as the key in the sparse histogram. We added a separate histogram for each CDP client type and started counting how often each CDP command is being used. Now, let's look at some of the results we got. Looking at the domain level and only at Chrome extensions, a bunch of CDP domains were not used by extensions at all. Next, we have a handful of domains which are used very rarely. We recorded less than 100 command calls per month for these domains. The usage of the security domain is interesting. The only command being used there is set ignore certificate errors, which does exactly what its name suggests. This seems suspicious and could potentially be abused by Chrome extensions. And finally, we have a bunch of domains with high usage numbers by Chrome extensions. So what are our conclusions from this analysis? First, we want to disable access to a bunch of CDP domains for Chrome extensions. This applies to all domains which are never or very rarely being used currently, as well as questionable domains such as the security domain. These changes are currently in flight and will significantly reduce the CDP attack surface. In a second step, we want to look at individual commands instead of the aggregation at the domain level. Similar to the restrictions on the domain level, we could prevent Chrome extensions from accessing individual CDP commands. And that's it. Please feel free to reach out if you have any comments or questions. Bye!
Years ago, I introduced the Web USB API at a BlinkOn talk in Munich. Since then, we've shipped APIs for Bluetooth, USB, serial, and HID devices. Today I'm going to give a brief walkthrough of an application using the Web HID API. I'm sure that in 2020 my partner and I weren't the only ones who got suddenly interested in understanding ventilation. Since we exhale CO2, measuring it is a decent proxy for how well a room is ventilated. This cheap CO2 meter is powered over USB and will show the current concentration in parts per million. It also comes with a data logging application. This application is Windows only though, and so I wanted to see if I could read the data myself. Communicating with random USB devices like this can be difficult without documentation from the manufacturer, but luckily someone on Hackaday already did the reverse engineering to understand how the application communicates with the device. It turns out this is an HID device, so I could try to use the then experimental Web HID API. First off, what is HID? This is a high-level protocol for USB and Bluetooth devices that provides human interface. It allows the device to describe the kinds of buttons, axes, etc. it has, so a generic driver can support any kind of mouse, keyboard, or gamepad you happen to connect. The Web HID API allows web applications to support exotic or non-standard HID devices that go beyond what the keyboard event, pointer event, and gamepad APIs can handle. For historical reasons having to do with the APIs Windows applications could use to communicate with peripherals, using the HID protocol was the easiest option. So lots of weird things like this CO2 meter are HID devices even though they don't have anything to do with user input. So, how do we use Web HID to connect to this device? First, the site needs to request permission by asking the browser to show the user a list of compatible connected devices. For security and privacy, until the user selects a device, the site doesn't know anything about devices that are currently connected. This particular device requires the computer to send some configuration data before it will start reporting readings. I wouldn't have figured this out on my own, but luckily the author of the Hackaday post figured it out. The send feature report method lets the site set these kinds of configuration options. After being configured, the meter starts sending data. HID devices generate something called an input report whenever they have new data to report, like when the user presses a button. In this case, input reports are generated whenever the meter has a new reading. The first byte tells us what kind of data it is, temperature or CO2, and after some unit conversions, the next 2 bytes provide the value. I'm glossing over a lot of details. The Hackaday post covers more of how the author figured out the structure of the data sent by the device. Putting all this together, I now have a simple data logging application that I can run on any desktop browser. These device APIs are really convenient for building simple UIs because you have access to all the power of HTML and CSS. I could make this prettier with a JavaScript visualization library if I wanted to. Thanks for listening. Please reach out if you have any questions, and please share cool demos that you build.
Hello, my name is Mike Taylor, and this is part 2 to my BlinkOn 15 lightning talk. Back then, the change from 2 to 3-digit browser versions was imminent, but we didn't really know how bad it could be. In order to raise more awareness, we co-published a pair of blog posts on web.dev and Mozilla Hacks jointly with our friends at Mozilla, who also coincidentally just shipped Firefox 100 this week. This got some pretty good pickup in the press from all my favorite tabloids. And during the actual rollout of M100, we did learn about some sites breaking due to UA parsing bugs. But those sites were pretty receptive to outreach, and most of them have been fixed today and were fixed within just a couple of days. But there's actually a darker side to the story that's less well known. Dramatic pause. So as luck would have it, I got tagged on a tweet back in November where we learned about an energy website in the UK that was returning 403s for all 100 users. But it turned out to be not just the single site that was breaking. Instead, all the sites using this site building platform called Duda parsed 100 as 10 and would return a 403, considering all the traffic to be invalid and insecure. As far as we know, this was about 1 million sites that were broken. So luckily, through the magic of LinkedIn, we were able to get in touch with the CTO of Duda, and they fixed the bug within just a couple of days. So we didn't have to consider any other more drastic mitigations in the format of the UA string. After Duda, a jQuery browser detection plugin was the most problematic. Last fall, we knew of about 2,000 broken sites. But as of today, only 37 still have this script in place, which isn't so bad. So here are some of the lessons we learned from this effort. One, flags for debugging remain awesome. We had a flag to turn on version 100 ahead of time, and then we had a flag to change the version back to 99 so you could test and verify where the bug was. Anytime we can blog with our browser vendor friends, that is great. And point 3, given enough time, compat bugs will trend to 0, assuming they're well maintained, which may be acceptable depending on the level of severity of the breakage. And point 4, LinkedIn still is great for outreach after GitHub. So a ton of people helped with this project. Thanks to everyone listed here. If you're sad you didn't get to participate, we get to do this again in about 75 years when Chrome 1000 ships. So reach out to my kids. Thanks, everybody.
Hi, I'm Ian from the Chrome Speed Metrics team. One of the responsibilities that our team is charged with is the maintenance and evolution of the specs and code behind the metrics that people use to measure the performance of their websites. The most critical of these are the core web vitals: largest contentful paint, first input delay, and cumulative layout shift. Site authors and partners rely on the integrity of these metrics to ensure that users are getting the best possible loading experience and that we're reporting them correctly when they're not. But suppose we want to make a change to some code around LCP. Maybe we've seen a correctness issue, or not counting large images if they started as transparent. Maybe we've seen evidence that people are using that to game the metrics, and we want to fix that to ensure that the metrics stay trustworthy. We believe this is currently a small change and should be correct, but how do we prove it? Making changes to this code is tricky, since the most likely case for bugs is not that you cause a browser crash, that would be easy, but that you introduce a subtle flaw in the reported values and they become inaccurate. And if we don't notice that, we risk losing the trust of our partners and site owners to measure the state of the web. So how do we make sure that we get it right, or at least minimize the chances of getting it wrong? How do we show that a change to code is safe to launch? Well, we measure. We have lots of UMA and UKM data from real Chrome usage, and it contains all the metrics that we're concerned about. So before we launch, we set up a Finch experiment. We add code to record the metric the new way with the flag enabled and the old way without the flag. We can see the effect that the change has. With very careful A/B testing on actual users, and we can compare it to reports from users without that change. We start off with 50%, half of all Chrome Canary users. But here we're really just looking for crashes or massive outliers, any reason to suspect that something is terribly wrong. We can't actually rely on statistics here, so the sample sizes are just way too low. But if that's okay, we let it go to 50% of the beta population. We start looking at any real shifts in the aggregate stats. If any of the core metrics shift by more than a small percentage across the entire beta population, then we'll look into what might be causing them. It's a much higher population than Canary, but it's still relatively small, and the people using it don't necessarily have the same browsing patterns as the global stable population. So assuming that we've already tested for correctness, we're really just looking for unexpected big swings at most. But if it looks okay on beta, then finally we let it go to stable. Usually at most 1% of the Chrome stable population. Here's where we're really looking at the statistics. We use SQL queries across all of the anonymized data to look at aggregate changes to the metrics, globally, per origin, even per URL. If we see unexpected changes, we can pull back the experiment and figure out what we need to fix. On the global scale, we said we thought this was a small change, affecting just a few sites. And if we see otherwise, we're definitely going to want to talk to people before proceeding. Per origin, we're looking to see who's going to be most impacted. Do we need to do outreach, DevRel, to let people know that they might see significant negative or positive changes to their core vitals? And per URL, we hope to see some big changes here. So what changes are most affected and why? Assuming that our code change actually does something, we should see an effect on some sites. So does the code change make sense? Is it in the right direction? If all of that looks good though, if we're making the right changes to the metrics on the right pages and we're not disrupting the whole ecosystem, then we get to ship with confidence and maybe cake.
All right, so thank you very much for many amazing updates and heartwarming messages. I am excited about the lightning talks because we have speakers from multiple organizations, including Microsoft and Igalia. So we had 11 non-Google speakers this time. So please send another round of applause to all the speakers. Thank you very much. So if you are interested in some specific topics, you can directly reach out to the speakers. Please do that. So next time, I hope I can see you in person. So see you again at the next BlinkOn.
Can't believe I'm continuing to be muted. Thank you, Kentaro, and thanks to everyone who submitted a lightning talk. So much cool stuff as always. Given this is only our second time hosting BlinkOn on Hopin, I want to call out one of my favorite features. If you click on someone's profile under People, you can send them a message, invite them to a video call, or schedule a meeting with them all directly in Hopin or in ChromoSpace. Now, I wasn't kidding when I said I'd be giving everyone a call to action. Right now, I challenge you to reach out to those 1 or 2 people I had you picture earlier and give them a quick invite. Catch up with them before the end of BlinkOn. All right, you've got an opportunity to chat with them right now, as the sessions will not be kicking off until 8 o'clock Pacific, about 15 minutes from now. So for now, please enjoy a short break, and I hope to see you chatting with a new person.